Hi there, welcome back to the formulaic approach. Now in this video we are going to be talking about how to derive the continuity equation. Now you already know that the continuity equation is associated with laminar flow or streamlined flow. Alright, so and the common expression is A1, or the general expression rather, is A1 V1 equal to A2 V2. Now actually the relationship between A and V can simply be referred to as flow rate, right? The flow rate of a fluid inside a tube. Now, and it's given by the volume per unit time, that is volume of fluid flowing per unit of time. Given that volume, this can be proven already that volume is area times height, okay, per unit of time, okay, and h over t, or distance over time, that is velocity, right? So we have av. That is just the proof for this. But actually, to derive the continuity equation, we have to look at two sections of a tube within which a fluid, a non-viscous fluid, is flowing. So for example, if I have a tube that looks like this, right, so this fluid is going to, this portion of the tube, rather, this is my tube, okay, this portion of my tube is going to have, if I pick a portion of this tube, this portion, the concentric area there is going to be given by A1, okay. If I pick another portion here of the fluid that is flowing here, given that the fluid actually fills this entire tube up, okay. If I pick a point here, this is going to be A2. Make sense? Now this guy here is going to have a particular speed at this point, isn't it? And this guy here, the fluid, is going to have a particular speed at this point. The speeds at any point is going to be given by ds over dt. Why am I parameterizing this way? Because velocity is already distance over time. So, but because the fluid that we're considering is a very tiny amount of fluid just given over a given area. So because the area is very small, so the distance that is moving is very tiny amount of distance and over a very tiny amount of time interval. So as well, so but this will be a v1, velocity 1, and here will be velocity 2. So v2 equal to what? ds over dt as well. Do you understand now? Okay, so the fluid that is moving, okay, is very tiny, like I said, so we parameterize it as dm, okay, and recall that the constant for any fluid is its density. So the density of a fluid is given by the mass of the fluid over volume. So the mass that is flowing at this point is going to be dm, hence our formula is going to be rho dv, okay. Now, why is it not small density? Because the density is not changing. It's constant for any fluid, but the volume is not constant because we are considering a very tiny volume given the tiny amount of mass that we are considering. If this is the case, then these are pivotal expression then. So in our pivotal expression, we know that we have dv there, so that is the velocity. We have the volume rather. So we have to get an expression for that tiny amount of volume. So you already know that volume is area times distance. Okay, so the volume of that fluid at this point is going to be the area at this point times the tiny distance that is moving, right? So that will be times ds. Since I already proved to you that area, you know, of course, that volume is area times distance or area times height. So in that case, then we have area, which is in this case A1, given that this is also dV1 times ds. So at the end of the day, we are going to have the expression for dv will be dv1 equals a1 ds. Now from here, from this one, let me call this equation 1, call this equation 2, call this equation 3. So from equation 1, I know that ds is equal to v1 dt. Don't misconstrue this and this. This one is volume, this one is velocity. In physics, small v is velocity, big V is volume. So I'm going to substitute this guy for this guy in that equation 3. So we have that dv1 is going to be a1 V1 dt. All right, A1 V1 dt. So this is going to be the expression for the V1. And in equation 2, I already have that dm, the small mass of liquid or fluid, is A1, is rho dv1. So if that be the case, then I'm going to substitute again for dv1 such that dm becomes rho A1 V1 dt, rho A1 V1 dt. All right, so this is going to be for our fluid. Now, the mass of the fluid that we are considering here, we are going to make sure that it is the same as the mass of fluid that we are considering here. So if that is the case, then we know that if this is dm1, then dm2 is going to have the same property, rho A2 in this case, velocity small v2 and dt. Okay. Now also we know that now I'm now saying that if dm1 and dm2 were the same, then we could say that rho A1 V1 dt is equal to rho A2 V2 dt. Then we can cancel out expressions. Dt takes care of dt, rho takes care of rho, and we have A1 V1 is equal to A2 V2, and this is the continuity equation. You also subscribe to the channel and click the bell notification to get notified whenever I drop a new video. Thank you. Why are you watching? Do you understand it? Okay.